Hello, I hope you're doing well. In this video, I want to talk about how to design a linear actuator. So my experience with this is that I have been working on designing some linear actuators that I'm using for my project Jugglebot, and I want to just make a video that explains how to do all of this, because all of this information exists on the internet, but it's in weird forums and it's sort of like nestled away in, for what was for me, a difficult place to find. So I want to try to explain in a sensible way how you can go about doing this yourself if you ever need to design a linear actuator for your own purposes. And yeah, so hopefully it's helpful for someone, because I know it would have been for me about 2 weeks ago. Before I get too into the analysis here, I just want to mention that if it seems like my lip is a bit inflated, it's because I had the good luck of getting stung by a bee on my bike ride this morning. So hopefully that is not distracting. Just bad luck. The first thing that I want to talk about in this video is how to actually pick the most important components of the linear actuator, which are the motor and the screw that you use to actually drive the linear motion. And then after that, I'll be talking a bit more about the qualitative aspects of it, so like how you can design the joints and bearings and putting in limit switches and that sort of thing. So without further ado, let's get into the motor and ball screw speccing. So when it comes time to design your linear actuator, you're probably going to be looking to achieve a certain speed of actuation and a certain amount of power or force of that actuation. And as we will find out soon, these two quantities are related to each other in a not so helpful way. So you might be able to prioritize, you might be able to get an actuator that will have lots of speed and very little power, or vice versa. And getting a balance between these requires a bit of understanding of what's actually going on here. The easier of these two quantities to analyze in a bit of detail is speed. So let's have a look at that one first. So we ultimately want to know how much speed we can get out from our linear actuator. So if this is our little hub part, we might have the plunger coming in like this, and we want to know how quickly this can move in and out. So what we want to know is the velocity of the plunger on its way in and out. We can find this pretty readily by just multiplying the angular velocity of our motor itself. So this is omega, so this is the angular velocity of the motor. And this is typically written in RPM, but if you're doing any sort of calculations with this, you should probably convert that to radians per second. And if you're not familiar with that conversion, you can just use an online calculator, and it's pretty easy to do. So we multiply our angular velocity of the motor by the lead of our screw. And what the lead is how far you will move for every rotation of the screw. And there's a really helpful animation that I'll put up on the screen now that shows how this works. And what the lead is, mathematically, is the pitch of the screw, which is just how much distance there is between each rotation of the screw, and you can measure that just with a ruler or some calipers, multiplied by the number of starts, or, said another way, the number of screw threads there are. To make sure that our equation here is correct, let's just have a run through and think what we're going to get out when we multiply these two terms together. So this omega is our angular velocity, and that's telling us how quickly the motor is spinning. So that's measured normally in radians per second. Our lead is telling us how far we are moving for every rotation. So this will be meters per rotation. And we can see that if we multiply these two together, what we end up with is this mess of radians times meters divided by rotations times seconds. And what we want to get out is, of course, meters per second, because that's what velocity is. So we've got this mess out the front here, which is screwing up our units. So we're definitely missing something here. And what we're missing is a conversion between the rotations per radian, because these two terms here are using different units. This omega has everything defined in terms of radians, whereas the lead has the angle part defined in rotations. So we need to add a factor in that puts these into the same units. So what we can do to fix this is just multiply this unit mess that we've got over here by what we want to get rid of. So we want to remove rotations on the bottom, so we can put rotations on the top of our multiplier, and we want to remove radians from the top, so we can put radians down the bottom. So if we multiply this stuff here by some rotations per radian factor, then what we'll get out is our nice meters per second, because this will cancel with this, and this will cancel with this. And we'll be left with just meters per second. So what is this rotations per radian factor? Well, another way to put this is how many radians are there in one rotation. And if you're not familiar with radians, then you might want to look them up, but it doesn't really matter too much. But the TLDR is that there are 2 pi radians in one rotation, which means that our rotations per radian term is just going to be the inverse of this. So 1 on 2 pi rotations per radian. And so we need this factor in our equation up here to just balance all the units out and to make sure that everything is using the same terminology. And so if we multiply our angular velocity by our lead of our screw, and then we multiply all of that by 1 divided by 2 pi, we will get out the speed of our motor. This is all well and good if all we're interested in is the velocity of our linear actuator, but quite often there are much bigger restrictions with regards to the force that we're getting out from our linear actuator. Because even if you'd run this calculation and you find that your linear actuator might be able to move at like 2 meters per second, if you have a really heavy mass attached onto this, or a really weak motor that might be able to spin really fast, it might be able to meet the angular velocity that you need, but it might not have the torque required to actually push with the amount of force that it needs. So to figure out whether or not our motor is actually strong enough to run the linear actuator at the speed that we need to do some power analysis. I think the easiest way to do this power analysis is to start off by comparing the power that we're getting out, which is what we're ultimately concerned with the power coming in. And what I mean by this is how much power can our linear actuator push with versus how much power is our motor providing to the linear actuator. And unfortunately, because we live in a world with friction, this equation is not quite true as it is right now, because there are going to be some losses in the system. There's going to be friction involved, and there's going to be heat and sound and other forms of energy losses. And so what we need to do is multiply our power coming in by how efficient our system is. And efficiency is normally written with this symbol eta. It's a very weird symbol, but there you go. And to get a rough idea of what our efficiency should be, we need to have a look at what type of screw we're using in our linear actuator. Because there are 2 main types here. There are ball screws and there are lead screws. And these are very similar. However, ball screws have mechanical balls that roll inside a little mechanism, and those massively reduce the friction, whereas lead screws are basically just a nut on a thread. And so there's a lot of friction involved in those systems, and thus the efficiency is a lot lower. From what I've read online, ball screws can reach efficiencies of up to 90 to 95%, which is pretty damn good if you get good quality ones, whereas lead screws generally fit within the range of 20 to 80%. There are, of course, other places where we might lose energy in our system. However, these values will give a first pass at an approximate estimation of how efficient your system should be. If you've designed everything else well, then there should be minimal loss outside of these ball screws and lead screws. So we know approximately what our efficiency is, and now we need to look at what power we're getting out compared to what power we're getting in. We need to put these terms in more useful forms, because just how they are right now doesn't really help us with much, because they contain within them a lot of information that we can't actually get out in their current form. So to get that information out, we need to delve a little bit deeper into what each of these terms actually are. So let's start off with the power coming in for no particular reason. It doesn't really matter what one you do first. The power coming in is the power that's coming from our motor itself. So somewhere on our linear actuator, we will have a motor with a little spindle coming out, and that's going to be rotating at some given speed. And the power that that motor is outputting at any given instant is equal to its torque multiplied by the angular velocity that it is spinning at. And in case you're wanting to do these calculations yourself, you should, as always, use SI units. So the torque will be in Newton meters, and the angular velocity will be in radians per second. So that's the power that we're getting into our system from our motor, but what about the power that we're getting out? We need to put that in some more useful terms. And similarly to how our power in had one variable that was related to force, it's sort of like an angular force, and we had one variable that's related to speed, in this case angular speed, it's the exact same thing for the power coming out. But instead of using angular terms, we're using linear terms. So the power coming out is equal to the force multiplied by the velocity of our plunger. So that's this velocity from up here, from earlier. Keeping in mind that this force is ultimately what we actually care about. So now that we have our power in and our power out in terms of some more useful variables, let's put these both back into our main equation from above and see what happens. So we have force times velocity is equal to torque times angular velocity times eta. Ultimately what we care about here is the force. So let's rearrange for force. We'll get F is equal to eta times torque times angular velocity divided by the linear velocity of our linear actuator. We could use this equation in its form like this, and you would be able to pick the motor that you need to pick and everything like that. But I think it's a little bit more helpful to write this velocity, which is the velocity of our plunger, in terms of the motor and the screw characteristics. So that way our output force is purely in terms of the motor and the screw characteristics. Thankfully, we've already done the analysis for this velocity up here. We've already found that the velocity is equal to the angular velocity of our motor multiplied by the lead of our screw multiplied by 1 divided by 2 pi. So if we put all of this into our equation in place of V, what we end up with is F, which is the force out of our linear actuator, is equal to the efficiency of our system, eta, multiplied by the torque, multiplied by 2 pi, divided by the lead of our screw. And in case you're wondering, the omegas here cancel out. So there's one on the top and there's one on the bottom, and so they cancel each other out. So this is our final equation for how much force we can expect to get out from our linear actuator. Now remember that the force is not the only objective. We could have an actuator that can output an extremely high force, but it might be super slow. And so in reality, often there's a balancing act between how much force you can get out and how much velocity you can get out. So what we have are these two sort of governing equations for our force and our velocity from our linear actuator. And you'll note that the motor characteristics appear here in terms of torque and angular velocity. So what we can do to figure out if our motor is up to the task that we have for it is we need to know the relationship between torque and angular velocity. And that is where motor performance curves come in. So any motor will have a motor performance curve similar to this one here, where on the y-axis we have how much torque we can get out, and on the x-axis we have the speed of the motor. So we can see here that we've got the speed down there and the torque up here. So using this curve, we can figure out how much torque we can get out at any given speed. And this will allow us to figure out what the maximum force is for the given linear speed that we're getting from our linear actuator. So using a curve like this and these equations, we can figure out exactly how much force and speed we can get out from our actuator. The unfortunate thing here is that many hobbyist motors, at least all the ones that I looked at, do not come with this performance curve by themselves, because I guess for whatever reason the manufacturers haven't made it or haven't supplied it. So actually getting this curve is a whole other story. If you buy really professional Schmicko motors, then they probably will come with a performance curve like this, but if you're buying hobbyist ones, then it's unlikely. I'm actually planning on making a motor performance curve for the motors that I have bought for my linear actuators, and I'll be covering that in a video that I'll post sometime soon. If this whole exercise seems a bit too over the top to you, then have a think about what you can actually do with this information. Because what this is allowing us to do is to figure out exactly how hard we can run our system regardless of how fast we're running it. So that way we can always make sure that we're sitting just underneath this curve, because we don't want to be maxing everything out all the time, but we know exactly how hard we can push it before something is going to stop working, before the motor will stall or skip steps or whatever else. This will allow us to get the absolute maximum power out of our system that we possibly can. It's a much better way of doing things than just randomly testing and just having some cutoff value that's inevitably going to remove a whole lot of power from your setup for no real gain. Having this sort of understanding is extremely helpful with using your equipment to its full capacity. So that's that for the quantitative part of this analysis, and now we can have a look at the qualitative components that are important when designing your own linear actuator. The first of these is how to transmit the power from the push rod to the ground, ultimately. And depending on your application, you might have a really, really high force, so you might want to adapt this to be something a little bit different. But the way that I have done this was actually inspired by a solution that I found on a forum called the XSimulator forum, where people talk all about making simulating platforms for like using VR for race driving and for plane simulations, that sort of thing. It's actually a pretty cool forum, and there's a lot of information on there, and I will link to that in the description below. It was a very helpful forum for me to search through when I was designing these actuators. So this design was inspired by something that I saw on that. And the purpose of this design is to make sure that as little force comes down into the motor as possible, because motors are typically not very happy with having their shaft being pushed into them. So you want to minimize how much force is going straight down into the motor. And the way that this is done is there are two bearings in this little section in here, and these will transfer the force from the rod up here down into this printed part, down into these screws, and down onto the ground, removing any force at all from going straight into the motor. And that way the motor can just spin, happy as Larry, and not have to worry about any force going on it. It is a little bit important that you choose the right bearings for this, because normal bearings are not supposed to have high axial loads pushed onto them. So you need to make sure that you get some bearings that are suitable for this task. And when you're doing this, you should have a look into thrust bearings and angular contact bearings. Both of these bearings are designed to have relatively high axial loads and should be up to the task. While we're on the topic of bearings, it might be worth pointing out that I actually have two bearings inside here. So I've got the first is a radial contact bearing, which is designed to support axial loads as well as rotational loads. And then the second is just a normal bearing. And the reason why I've done this is that the first angular contact bearing will support all of the axial load, and then it will transfer that load out to the rest of the printed part. And then the second bearing will just allow greater support from wobbling, because with only one bearing, that's only about, I think is a 8 to 12 millimeters thick, something like that. It only has that much support, and so that way the rod might be able to wobble a little bit. And so just by having that second bearing there just gives it a little bit more thickness to hopefully support against that wobbling. The next thing I want to talk about is the number of rods that you use to support the main push rod. You can see here I have used 2 rods, while many designs that I've seen online use 4. And I'm not too sure why they've done this. I think it might just be because a lot of the threads that I was looking at are a couple years old, and 3D printing is a relatively new technology, and I don't think they were using 3D printed parts. So I think they just had to stick with 4 because that's sort of what you need to use when supporting motors like this, which have 4 screw holes. So I think that they just extended these rods the whole way up and didn't worry about adding any other ones in. I have chosen to use 2 because, well, first thing, these are threaded rods and they don't slide very nicely, whereas these are smooth rods and they do slide very nicely. And secondly, to minimize weight. So that by only having 2 rods, it's a lot smaller and has less mass to move around. Some of you might be concerned that by only using 2 rods, it's going to not be able to resist that sideways force enough, and these rods are going to twist and move around, which they really shouldn't be doing. But rest assured that these ball screws that I'm using seem to be quite good, and there's extremely little resistance in powering this actuator. So right now I can just spin the screw and it moves very, very, very seamlessly. Granted, I'm not spinning this at 1000 RPM, so it's possible that when the motor's actually spinning this, these rods might want to move, but they're pretty securely in there in the 3D printed part, and I really don't think it's going to happen. And if it does, I'll have to cross that bridge when I come to it. The next thing that I would like to talk about is the position of the limit switches that will allow you to control the exact position of the linear actuator. In my case, I am using stepper motors, so all that I will need to do is set the position once at the very beginning of the Jugglebot's operation. And then I should, unless it skips steps, I should know exactly where the linear actuators are at all times thereafter. So what I have done is I've put my limit switches down at the bottom here, nicely tucked away in here, so that as the motor spins down, it will bring the linear actuator down until eventually, if you can hear that, it clicks on the limit switch. Now this is nice because the limit switch is nicely tucked away and it's a pretty neat design, I think. But it does have a problem, which is that because the limit switch is right at the very end of the travel of the linear actuator, if there's any issues in the software or anything like that, then it's possible that this could overrun the limit switch and smash into the printed part down here and cause problems. Something would probably break, or the stepper would just start skipping steps, which would be ideal. But it wouldn't be good in any case. So for my purposes, I think this is fine because I shouldn't be running this hard enough where it will skip steps. And when this limit switch is being used, which is at the very like once I turn Jugglebot on, it will start to calibrate and it will be running quite slowly. And so there shouldn't be any software issues where it will overrun this switch. And I shouldn't be running it hard enough that it will ever skip steps. So during its operation. So that means that it should always know exactly where it is, and I can just make sure that it doesn't exceed too long and it doesn't go too short. So fingers crossed. If you want a more robust solution, then what you should do is put the limit switches in a place where the linear actuator can actually slide past the switch. And if you want to be really, really secure, then you can have two switches on either end. One is a soft switch where it tells the software, like, hey, you've gone too far, you need to turn back. And then you have a second further down hard switch, which will cut power fully to at least that one actuator and probably the whole system. That is much more robust because then you can make sure that nothing will overrun its limits, but it does require a bit more space. Like I can't mount a limit switch in a place where the motor can overrun it very easily with how everything else is set up. So I think this will work fine for my purposes, but just be mindful of where you put these switches in case you have a more industrial application or anything like that. Another thing that you'll have to consider, particularly if you have a quite long stroke of your actuator, so it can run really far up and down, is how to fix the end of your ball screw or lead screw in place. Because right now, I just have it freely in place and it can move around a little bit, not very much, but a small amount. And that might cause rattling inside the carbon fiber tube if it's not perfectly aligned, if it can sort of move around like that. So right now it's totally unconstrained, so it can just wobble. It shouldn't because I only have a relatively short stroke. But if it does, I've seen people have little 3D printed spaces, essentially, that go between the ball screw end part and the inside of your rod. And I'll put a photo on the screen now of what that looks like. And that just makes sure that the rod is nicely secured in place and won't be able to move around at all. So if I find that when this is actually in operation, particularly at high speeds, it might make a rattling sound of the ball screw hitting the carbon fiber rod. If that happens, then I'll put one of those spaces in and it should fix the problem. That problem will be greater with a longer stroke because then there's more length for that wobble to be accentuated over. The second last thing that I'd like to mention is how I've attached the ball joint to my carbon fiber tube. I am pretty happy with how this has worked because it's a nice, tight design. There's nothing really hanging out over the end, and it is very secure. I don't think it will be possible for me to pull this out. It's really not going anywhere. The way that this works is actually pretty straightforward. This 3D printed part at the end has an inner ring which goes inside the carbon fiber tube and is designed so that it gets slowly thicker and thicker, only just by a very small amount as it gets longer, as it gets further in. And so then when you screw the ball joint screw part inside, it will push that against the carbon fiber tube and really secure it in place. It is, at the end of the day, just a friction fit, so it is possible that this could just slide out, but the force required to do that is far more than I can supply. So I think it's pretty secure. The last thing that I want to talk about relates specifically to Stewart platforms. So if you are using linear actuators to actuate a Stewart platform, you need to have a think about what joints you use at the ends of your linear actuator, because it's not immediately obvious, at least it wasn't to me, how this should be designed. Now, you might remember from my earlier design, I had ball joints at the tops and bottoms of every actuator, so these could actually spin on the spot. And that's actually not very desirable. I didn't really know this at the time, and to be honest, it didn't really matter with these actuators because they're so weak. But with more powerful motors, what can happen is that when the motor accelerates, it generates a bit of a kick and will start to spin. And that could cause issues with the cables getting tangled up, and you don't really want that to move around in a way that it doesn't need to. So this rotation is undesirable, and we don't really want to let the actuator do that unless we have to. On the flip side, we do want to allow some amount of rotation with respect to the platform, because as the platform moves around, there's going to be some rotation between the leg and the platform, and we want to make sure that that rotation is not jamming any joints up. So we want to allow rotation between the platform and the leg, while disallowing the leg itself from rotating about its longitudinal axis. The way that I've done this is by having a ball joint on the top, which will allow that rotation to occur between the platform and the leg, and having a universal joint down the bottom, which will allow the leg to move around in any direction that I want it to, but restricts rotation about its own axis. It does have a little bit of wobble right now, just because I haven't tightened everything up and at this specific joint yet, but when I've completely made everything, it should be a very tight joint down here. So this can move around everywhere where it needs to, and the ball joint will allow the leg to rotate with respect to the platform. I feel somewhat obliged to mention again the XSimulator forum, because that's where I got the idea of using this combination of joints. And yeah, I strongly recommend that if you are designing a Stewart platform for whatever purposes, check out that forum, because there's a lot of really good information on there, and it's a very, very, very good resource. I'll put a link in the description. So that just about covers everything that I have learned about designing linear actuators in the last couple of weeks. This is definitely by no means a comprehensive guide, and you should be carefully thinking about every single design decision along the way and not just copying everything that I've done, because it's pretty likely that I'm going to have to change some stuff on here at some point in the future. With that said, I hope that this has been somewhat helpful for people out there, and yeah, I hope that you learned something. I will see you in the next video, and have a good one.